Good morning, relativity friends. Um, this is something you run into when you're studying Riemannian geometry uh, or general relativity, the fundamental theorem of Riemannian geometry. And I needed to understand it. So that's why I did this. It states that for any Riemannian manifold, there exists a unique affine connection that satisfies two conditions. So today we want to do condition one, which is metric compatibility. It states the covariant derivative of the metric tensor is zero in all directions. That means the metric tensor's components maintain their values under parallel transport. Okay, those are a lot of words. So let's actually first of all, do it abstractly, and then we'll do an example. Okay, so first thing we have to do is write down our covariant derivative of a metric, the tensor. Okay, now look at this. We've got the free indexes, and they're all in the covariant position, right? So when you take the covariant derivative of a covariant, the tensor, you need two connections, this one, and both are negative. So ever how many indexes you have to have one of these. So if it's 3, it'd be 3. If one is in the contravariant position, remember, then one of these would be positive. All right, so we take our normal partial derivative as normal, and then we have our two connections, and you see the free indexes here, right? They're all in the covariant position. So here's K, J. So you pick one to go with this, you pick the next one to go with K. And then you fill in the remaining, the free index. And then this M's become your summation indexes, okay? So we've all done this before. And it's fun. Now, what is the metric, the tensor? Well, it is the inner product of the basis vectors, right? Remember that? So let's break this out. Let's break this out here by itself and write it with the partial derivative of the basis vectors with respect to a coordinate. So we have to use the product rule here, the first times derivative of the second plus the second times derivative of the first. Well, if you've been looking at this stuff for a while, you instantly recognize these, right? What are these things? Those are actually the definition of the Christoffel, the symbols. Remember, the derivative of a basis vector with respect to a coordinate. So this is the derivative of a vector is a vector, which can be expressed as a linear combination of its components and basis to vectors. So that's what this is. And once again, you have to be careful where you put your indexes, right? So both of these are covariant, lower. Then you got your summation index, because you know this is a multi-valued term. So there's going to be more than one of these, depending on how many dimensions that you have. Okay, so let's put that back in. But this is the unique affine connection, the Levi-Civita connection. Okay, so let's put that back in there and put it back in our first equation. So now we've got all of this. Now, these are just the metric, the tensor, right? Let's back up and make sure everybody, okay, because I stuck these words in the middle. Okay, so we defined these connections. We put them back into this. Then we took this whole thing and put it back in here, right there. Okay, so that's what this is. So em.ei is just gmi, em.ej is just mj, gmj, right? Now remember, the metric, the tensor, is symmetric about the diagonal. So gmi is the same as gim, right? And here's the other thing that we're going to do now, but we're going to learn why later, is that the Christoffel, the symbols, the Levi-Civita Christoffel symbols, are symmetric about the lower indices. So gamma mjk is the same as gamma mkj. So you see this cancels that, and you get 0. So there you go. Now let's do an example. Okay, let's work in polar the coordinates. So here are the only two non-zero elements of the metric, the tensor, and here are three non-zero components of the Christoffel, the symbols. So we have five things here to work with, and here's our generalized equation. Now, if you work all of these out, which I would encourage you to do that because it's really good practice with indices, all of them have just zeros everywhere except one. Let's just do the one because we don't want to be here all day, do we? Okay, which is the covariant derivative of gr theta with respect to theta. Okay, so you just follow your indices. You see that k is theta, I is r, j is the theta. So you go through here and you fill in all of your free indexes first. Now you know we're in polar coordinates, so it's two dimensions. So there's going to be two of these and two of these. So you write down four of these things. You put negatives in front of all four, and you fill in your free indexes the first, k, j, I, in every one of these. Then it leaves your summation index. So in the first case, it's going to be r. The second case is going to be theta. First case r, second case the theta. Okay? So now we have this expression, and we only have these non-zero things to put into it. So let's do that. Okay, well, this is 0 because I don't have one. This is minus r. This is 1, 0, 0. Don't have 1, 0. That's 0, we know. Okay, here's one. Is minus 1 over r because there's a negative here. And g theta theta is r squared. Okay, now we got some business here. Okay, let's get rid of all that stuff. We got r minus 1 over r squared. Takes out one of the r's, r minus r is 0. So there you go. This is a real example of the covariant derivative of a metric tensor component, and they're all 0. If you do every one of them, I promise you they're all 0, right? So this is the first condition of the fundamental theorem of the Riemannian geometry. The first condition is metric compatibility. Okay, so next time we're going to do the second condition. All right, thanks for watching. See you later.